Hello everyone, this is Yulin Wang. I'm glad to present our CVPR paper AdaFocus V2. Recent years have witnessed an explosive growth of online videos. Such large amount of data has fueled the demands for automatically recognizing human actions, events, or other contents within videos. Deep learning is still an effective solution for video recognition. However, processing videos with deep models is far more inefficient than images. In practice, computation directly translates into power consumption, carbon emission, and practical latency. A key challenge is how to make deep learning-based video recognition more efficient. The recently proposed AdaFocus network reveals that reducing the spatial redundancy yields promising results for efficient video analysis, namely dynamically identifying and attending to the informative regions in each video frame. In specific, AdaFocus first takes a quick glance at each frame with a light-weighted global CNFG, and then use a policy network pi to localize the most informative image patch. The patch is processed with a high-capacity local CNFL. Due to its reduced size, considerable computational cost can be saved. Finally, the local and global features are concatenated and fed into the classifier FC to get the recognition results. An important problem for AdaFocus is how to train the policy network. The original AdaFocus V1 network needs to be trained with a complicated 3-stage training pipeline, resulting in long training time, suboptimal solutions, and being unfriendly to users. In this paper, we reformulate the training of AdaFocus as a simple one-stage and end-to-end trainable algorithm. We first introduce a differentiable interpolation-based patch selection operation. We assume the policy network pi outputs the continuous center coordinates of frame patches. Then we can obtain the coordinates of each pixel in the patch. In the feedforward process, we can easily calculate the values of all pixels in the patches through the differentiable bilinear interpolation. In the backpropagation process, it is easy to compute the gradients of the patch pixels. Following the interpolation process, we can obtain the gradients of the outputs of pi. With this differentiable operation, end-to-end training has been feasible. We can minimize the frame-wise cross-entropy loss. However, such a straightforward implementation leads to a degraded test accuracy. To solve this problem, we developed 3 simple but effective training techniques. First, FG and FL are only indirectly supervised by the gradients from the classifier FC. This leads to a lack of supervision. We attach two linear classifiers to their outputs to provide auxiliary supervision signals. Second, the patch selection process is deterministic. The local CNFL only has the access to a single patch. This leads to a limited input diversity. We address this issue by augmenting the training objective with a loss corresponding to the randomly selected frame patches. Finally, pi and FG are simultaneously updated. We observe that the gradients backpropagated from pi will interfere with the learning of FG, leading to an unstable training process with slow convergence speed. We solve this problem by stopping the gradients before pi. One can observe that with these 3 techniques, our one-stage formulation AdaFocus V2 outperforms the 3-stage counterpart eventually. An advantage of AdaFocus is that it can be augmented by simultaneously reducing the spatial and temporal redundancy. We achieve this by performing early exit for some easier videos, which can be correctly recognized with a subset of frames rather than all. Our approach does not need additional reinforcement learning, but achieves competitive performance. Empirically, AdaFocus V2 reduces the training time by more than 2 times while dramatically improving the accuracy. Compared with the best baselines, our method reduces the computational cost by up to 3.6 times without sacrificing the accuracy. On FCVID and mini-kinetics, similar observations can also be obtained. Here are some visualization results. AdaFocus V2 focuses on some task-relevant regions, such as the violin and the dog. For more details, please refer to our paper.